We've been talking about magnetic forces. Let's talk about some of the interesting ways they're used in applications. The first one is the cyclotron, invented right here in our backyard at Cal Berkeley. This is a particle accelerator. There are two sections where there's magnetic field, and those are called Ds because they look like the capital letter D. I'll make my magnetic field coming out of the page. These two plates are connected to a source of alternating potential difference. If we release a charged particle at the center, I'll make it a positive charge. There's an electric field set up in this region, and the electric field is going to point at some point in time in that direction. That accelerates this positive charge upward. So when it enters the region of magnetic field, it has some small velocity. A positive charge moving towards the top of my page in a magnetic field pointing out of the page creates a force, a magnetic force on this charged object that causes it to curve and move in a circular path. And so it gets back to the region where we have the alternating potential. And by the time it gets back to that region, the alternating potential has flipped, and now our electric field points the other direction. And so our charged particle gets accelerated through this region, and it picks up some speed, and now it's moving a little bit faster than it was in the previous magnetic field section. And so it's going to follow a curved path that has a slightly larger radius. By the time our charged particle makes it around to our region where the electric field is, potential source is alternating. Now the polarity's flipped, and the particle gets accelerated through this region because our electric field is pointing up again. And it picks up speed, and now it's going even faster than it was before, and it follows a larger radius path. And by the time it gets to this region, the power supply is switched again. The source of potential difference has switched polarity. The electric field is now pointing down towards the bottom of the page, and so our particle gets accelerated in that direction, picks up speed, and it's going even faster than it was before, and now it follows a larger diameter path until it leaves the cyclotron moving at a fairly high velocity. You might be wondering, well, how do they time that, switching the potential difference every time, just as the particle's getting back to that region where the electric field is? And the answer is, you don't have to time it. The particle always takes the same amount of time to pass through the magnetic field region. Because the particle is moving very slow when the radius is small, the time it takes to complete this small radius path is exactly the same as the time it takes to complete this path, even though the radius is much larger now. And the time it takes to complete this path is also the same as the time it took to complete the other two paths. So switching the potential difference just has to be done at a regular interval. And the invention of the cyclotron at UC Berkeley and all the work they did with it afterwards won the University of California and Berkeley quite a few Nobel Prizes in physics. The next application I want to talk about is the velocity selector. The velocity selector is used in a number of things. Some mass spectrometers use them, and you may have used one in one of your chemistry classes. We have a source that creates charged particles and accelerates them across some kind of potential difference, and the charged particles come out with some velocity. But it's really hard to get a finely tuned velocity. There's going to be some spread in the velocities of these particles coming out of our source. We want to fine tune it a little bit. So we create an electric field in this region of space. And I'm going to make my electric field point down like this towards the bottom of the page. So if our charged particle is positive, it would feel a force from our electric field, and it would want to go in that direction. We also put a magnetic field into this region of space. I'll make mine into the page. A positively charged particle moving through this magnetic field would feel a force toward the top of the page. Let's draw a free body diagram for our positively charged particle. There's a force towards the top of the page due to its interaction with the magnetic field, and that's going to be QVB, and because they're at right angles to each other, we just get QVB. And we're going to get a force towards the bottom of the page due to its interaction with the electric field, and that's just Q times the electric field. One of these forces is constant. The electric force is constant. The magnetic force depends on the velocity of our particle. So if our electric force is equal to our magnetic force, then the particle moves in a straight line. That means the particle moves straight through, unaffected by those fields. So the velocity has to equal the electric field over the magnetic field strength. If the velocity is equal to that special value, it makes it through. What do? We build a wall over here with a little hole in it at the center. If the particle is traveling in a straight line, it makes it through that hole. If it's traveling too fast, then the magnetic force is bigger than the electric force, and we end up with a particle that curves up toward the top of the page and crashes into our wall up here. And if the particle is moving too slow, the electric force is bigger than the magnetic force, and it curves and hits our wall down here. So it only makes it through if the speed is just right.